In this video, we're going to look at something very closely related to the arithmetic sequence from the earlier lesson. We're going to be talking about what happens when we need to add all those numbers up. So an arithmetic series is just the sum of the terms that you get in an arithmetic sequence. So arithmetic sequences, you might be given a formula like this. When you plug in your numbers, k equals 1, k equals 2, k equals 3, you end up with a pattern of values. So that's what creates the arithmetic sequence. Now we're going to look at what happens if we need to add all those numbers up. And this actually comes up more than you might expect, because there are a lot of times where maybe it's like the number of seats in a theater or in a stadium. And a lot of times there's a pattern for how many more seats there are from one row to the next. So here I can see that I'm just adding those numbers together. However, we do have a formula that can be used as long as you have some very specific information about the sequence you're adding up. So the formula here is for the sum of a finite arithmetic sequence. We cannot use this if we have an infinite sequence. We have to have a specific beginning and ending point in our terms for us to be able to add them all up and get a single finite answer. So the numbers we need, n is how many terms there are in the sequence. So if you're adding up 20 numbers total, then n would be 20. We also need to know the first term in the pattern and the last term in the pattern. We have to use a sub n to represent that, because one sequence might only have 10 terms, another sequence might have 30 terms. So whether it's a sub 10 or a sub 30 will change, but keep in mind that that number of the subscript should match the number out front. So it's always just referring to the last term in your sequence. And then we're going to end up dividing by 2. Now, if you're in a situation where you don't have access to the formula, maybe you need to know the formula yourself, I like to point out that mathematically you can think of this as finding the average of the first and last term in the sequence. So you add those two numbers up and divide by 2. And then we're multiplying by how many numbers there are in the pattern altogether. But now let's look at some examples of calculating an arithmetic series. So one of the setups that's common for an arithmetic series is they give you the individual terms in the sequence, and then they just say they want you to find the sum of all of them. Now, a lot of times what happens with these questions is we are missing one of the pieces of information from the formula, either the number of terms, the first term, or the last term. Now, in this case, I know what a sub 1 is, and I know what a sub n is. But if I'm thinking about the formula on the previous image, I need to know how many numbers there are. I can't just count them up because they didn't list all of them out. And so that's pretty common. A lot of times there are so many numbers, they just do like a dot, dot, dot to save some space. And then we need to figure out how many there are in this case. So to do that, we're going to go back to the explicit rule from arithmetic sequences. So in this case, we have a sub n will equal a sub 1 plus n minus 1 times the difference. Now I can see that the difference on these is subtracting 5 every time. So my difference value is negative 5. Oh, and here for a sub n, I should have gone ahead and plugged in. I know my last term in the sequence is 18. So this is from the explicit rule from arithmetic sequences. I'm just plugging in the numbers that I know, and I'm going to use this formula to solve for n. So everything from here is just going to be my opposite operations. So the first thing I would do is I would subtract 73 from the other side of the equation. And this is going to give me negative 55. I'm just going to rearrange this and write it as negative 5 times n minus 1. It's the same thing, because you can flip the order of two numbers being multiplied. So my next step, instead of distributing, I think it would be better to just divide both sides of the equation by the negative 5, in which case this becomes 11 equals n minus 1. And so my last step, I would just add 1 to both sides of the equation. So now I know that n is equal to 12. So this wasn't actually that huge of a number. I probably could have just kept applying the pattern and counted them all up that way. But you might end up with a situation where there are maybe 100 terms, and you really don't want to go through the process of counting them all up and potentially making a mistake. So using the formula is generally the safer, faster bet. So now we need to actually find the sum. So my s sub n, that's the formula for the sum, this is going to equal n times the first and the last terms added together and divided by 2. Now, in this case, just to break this down one step at a time, if I add together the 73 and the 18, that's going to be 91 divided by 2. And since this is an odd number, what might be better to do is actually to kind of do the 12 divided by 2 instead. This is 12 over 1 times this fraction. So in a way, it's like I'm dividing this by 2 and then multiplying the answer I get by 91. So I can think of this as 6 times 91 now. And then if I just type that into a calculator or something, you would find that your total sum is 546 in this case. So that is what the sum of all of those numbers ends up equaling. Now let's look at another example. What if they didn't tell me what the last term in the sequence is, but they instead told me how many numbers there are in total? So this time what I have is the n value, and I still know a sub 1. I still know the first term in the pattern. But this time I'm missing a sub n. However, I can still solve for that by using the explicit rule for arithmetic sequences again. So this time the number I don't know is a sub n. It's still going to equal a sub 1 plus, and then this is n minus 1 times the difference, and I can still see that the difference is adding 4 every time, so I still know that d is a positive 4 in this case. So this has created another formula that I can solve, although this one I don't need to move things from one side of the equation to the other. I really just need to simplify what's on this side. So I know that my last term is going to be 5 plus, this is going to be 29 times 4. And then if we calculate this, this is going to be 116 plus 5. And then that means adding these two numbers together gives me my last term is 121. So that just gave me the last term in the sequence. But again, remember for the sum formula, I need to know how many numbers there are. And then it's the first and last numbers added together divided by 2. So I'm averaging the first and last number, add them up, divided by 2, multiplying by 30. Well, in this case, I'm going to think of this as 30 times 126 over 2. And then this one is an even number, so really I can divide either number by 2 if I want. Since this one is even, I'll just keep it within the fraction. So that would be 63. But if for some reason you would find it easier to do 15 times 126, you're welcome to do that as well. It'd be the same mathematically. So now I have 30 times 63. If I type that into a calculator, we should get 1890. So that number represents all of the numbers added up, the first 30 of them, because this didn't technically indicate how many we had total. So the sequence was going forever, but they told me that we're only adding 30 of them. That's what keeps this from being an infinite sequence or infinite series. And then let's look at one last example. What if they give you kind of a description of the numbers, but they don't actually list out the terms? So you might need to think a little bit about the description they're giving you. In this case, they say positive, odd integers. So I'm going to kind of write the sequence myself so that we can figure out what some of my missing numbers are. So if I just imagine a few of the terms, and then at some point I'll have a dot, dot, dot. I don't know what the last term is going to be yet. The very first positive odd integer would be 1. And then since we're only doing the odd numbers, I would skip 2, and then I would go to the number 3. And then if I kept doing that, skip the even number, so then this would be 5, and 7, and 9, etc. So now I know what a sub 1 is. And right here, we said that we're going to do 40 numbers total. And remember, I can look at what the difference is between terms to find the difference, the common difference value. So in this case, d is equal to 2. So if I need to find the last term in this pattern, I'm going to again return to my explicit rule and say that a sub n will equal the first term plus n minus 1 times the difference between terms. And I need to simplify this. So now I'm getting 1 plus 39 times 2. And this would be 78. But when you add on the 1, we get that my last term is 79. So we just found the last number in the pattern is 79. And then from here, I can again find the sum of all of these terms by using the sum formula. This is, again, a finite series that I'm calculating. The number of terms I have is 40. My first term was 1. My last term was 79. And we're dividing that by 2. I'm averaging those two numbers. Well, 1 plus 79 is 80. And if you divide 80 by 2, that actually gives you 40. So this is 40 times 40, or 40 squared, which means my sum for this one is going to be 1600. So this one didn't actually give me the terms. We had to kind of think about it a little bit more ourselves based on the description of what's creating this sequence. So that's it. Generally, you're going to need to use the explicit rule once to find one of the missing values, either the last term in the sequence or how many terms you have. That's generally the setup. And then after you find that, then you should be able to plug into the arithmetic series formula and find what those numbers all added up together equal. And that's it for this lesson. Thank you.